While I change the battery in the microphone, hopefully this works. Anybody have any questions on project 2 that we can talk about now before we get started? Yeah.
So the get token function in the Lexer.c code, that's how we're getting input in?
Yes.
Or do we have to use the C in
No, you shouldn't be reading anything, right? So the token, the Lexer is reading all the tokens in. So the whole point of the assignment is you're learning how to use the API of the Lexer, and that's so that's what you'll be using.
Okay.
Yeah.
Would you be willing to like record some kind of like how to debug with Emacs or Vim? Because I was having problems and I couldn't figure it out. I just ended up copying it into Visual Studio and using that, but I know I won't always be able to do that.
Correct. That's a good question. This battery also did not work. Anybody like a AV tech? Try the third one. Right, every so will
You're not putting it in upside down,
I don't know. I think it's a 9-volt battery. I think it only goes in one way, but I mean it did turn on, so it's not getting the. There we go. Hello? Hello?
Here we go.
How about now? Better? Going through? Okay, good. Okay, yeah, could I do that? Maybe. Send me an email. It takes a long time and it's hard to come up with a good example.
Or just a link to like a good resource that you've used or something.
Yeah, email me. I'll be happy to do that. Yeah, I mean, GDB takes a little bit of time to get used to, but it's time well spent because you use it. I use it all the time, debugging C code and C++ code. Okay, yeah. I've been actually meaning to do that, but it's just a time thing. Yeah. Cool. Any other questions? Project 2? All right. Last chance? No. Great. Okay, so where we left off, we were talking about parsing. So what's parsing? What do we care about parsing? What does parsing actually do? Yeah.
Turns a grammar into potential strings.
No. What is that? How do we take a grammar and turn it into strings? Derivations, yeah. So derivations, right? We can take a grammar, we can do a derivation to get a string. We can also create a parse tree from a grammar, right? We can generate a parse tree. That will also give us the strings. Parsing is essentially the opposite of that. What would be the opposite there? Yeah?
You're taking a string and turning it into a sequence of tokens.
No, that's lexing. Very close. After that, after we've lexed, we have a series of tokens. Now what do we want to do?
Match it to a grammar.
Yeah, match it to a grammar, right? And how do we know that it matches a grammar? Yeah. Oh, sorry.
I was going to say the exact same thing.
What?
The rules of the grammar.
The rules of the grammar. Correct. Yeah, so we want to build a parse tree from it, right? So we're parsing. Parsing is we want to take in either a string or a series of tokens, right? The series of tokens from the Lexer, and we want to say, did this string come from this grammar, right? And if so, what's the parse tree specifically for this grammar? So that's what we're studying now. We're studying now the reverse, right? So we've looked at, okay, it's pretty easy to, if you give me a grammar, right, I can, like this, expression.
You said taking a string and making sure it follows the rules of the grammar?
Yes, at a high level. That's what it's doing. Our goal is, from parsing, we want to take in a string, and we want to output the parse tree that that string corresponds to of the grammar. Right? So if we have these rules, we can very easily apply these rules over and over, right, until we've reached a string that has no non-terminals, only terminals, and we know that string is definitely in the grammar. But now we want to do the opposite, right? We want to start backwards. We start with the string and say, can this string come from applying any of these rules? Right, so is that easier or more difficult?
More difficult.
More difficult? Why?
there could potentially be multiple ways to parse a single string.
Yeah, there could be potentially multiple ways. Yeah, we'll get into that. It's kind of what we talked about with ambiguous grammars, right? There could be multiple parse trees. But actually, if you think about it, that could make our job easier, right? Because we have two targets or many targets to go to, right? We're starting at the string and we want to find the parse tree. So generating all these strings, right? If I asked you to generate, like write an algorithm to generate all possible strings that this grammar could create, would you be able to do that?
No.
No? You can't write one algorithm to do that? You may never finish, but it's pretty easy to write it. I mean, you just say, apply this rule, and if this rule doesn't fit, then the next time try this other rule, right? Just try all possible combinations of rules to spit out strings. But here we're going in the reverse, right? We're starting with this string 1 + 2 × 3, and we're trying to ask the question, is there any possible way, any possible combination of applications of these rules that creates this string, right? So it's actually a very, kind of a tricky problem. So let's kind of think about how we're going to do this. So what are the two things, what are the things I need to know to be able to do parsing? What are my inputs, let's say, to the parsing? Yeah?
You need your string of tokens, and then you need your rules of a grammar that you're going to try and match to.
Exactly, right? So you can't, like, parsing is specific to a given grammar, right? If you don't have the grammar, you'll never know, you can't answer the question if it matches or doesn't match, right? So we have our string. Let's go with, this will be our string for right now. And then we'll have the grammar S goes to big A or big B. And then we'll have big A goes to little a big A or A. And B goes to little b big B or B. So can somebody describe kind of what this grammar, what strings in this grammar looks like? Somebody over here in the back who haven't spoken in a while? Morning.
What are you asking?
What do the strings look like? Like what do the strings that this grammar produces or generates, what do they look like? Yeah.
Contains only A or B.
Yeah, contains only A or B's, right? So you can see that S, right? So S is the starting non-terminal. So we're going to start from there. All strings must be derived from S. And then it's going to be either A or B, and this will be any number of B, A's, any number of B's. So when we're parsing, we want to build a parse tree, right? This is our end goal. We want to build a parse tree. So what's the, well, as we're going to talk about, right? So S is always going to be the root node of our parse tree, right? Whatever the starting non-terminal is. Because every string that this language generates has to come from S, right? Any string that's derived has to be derived from S. So this is all we have. We have the rules, we have the string. How do I decide what's the child of S here?
Pick one.
Check the token.
Pick one, check the token. Which token? The first one?
Yeah.
The first token. So check A, but A doesn't match big A or big B, so how do I decide which one to choose?
The first one available.
Which of S's children could yield little a?
Which of these children could yield little a? What do you mean by yield?
Like which one would generate little a?
So
How does that help us?
it's possible to be A. So you pick A.
Possible to be A? Is it only possible to be A?
So if you check B, it starts with little b, so you don't have little b. Let me go backwards.
Well, out of the children, the only one that can generate little a's is big A. So in this case, it's simpler, but in a more complicated grammar, it would be.
We don't have to worry about other grammars yet. We're building up to that. But yeah, we want to think about this example, right, and try to see, okay, how would we actually do this? So remember, once again, we're building, our goal is to build the tree from the top down. We're doing top-down parsing. So we're going to start with S, right? So now we need to decide, okay, which one of these does S which one of these rules was applied to generate this string? Was it S goes to A or was it S goes to B? Right? And we can look at our input string, right? And we'll look at it left to right. And so we look at this first token, A. Say, okay, can big A generate little a's
Yes.
as the first token?
Yes.
Can big B generate little a's as the first token?
No.
No. So we know it definitely can't be S goes to B, right? And so now we can say, okay, S goes to A, right? So we know that's the first rule that's applied. But did I actually match this little a when I applied this rule in this tree?
It's just possible.
Right, it's just possible, right? We know it has to start with a little a, but we don't know that this rule here, applying this rule, didn't generate any terminals. Right? So we can't just move on and say, okay, we've matched that, now let's try to match here. Right? So then we go to this rule. A goes to little a, big A, or A. So which one of these rules apply?
The little
Little
a's.
a, big A, because we need to generate more tokens. We aren't.
Yeah, but how do you do it just with looking at this string, right?
String down length.
Well, if we only do little a, that's a terminal. We can't generate any more. We can't generate any more tokens from that. And since the string that we're trying to parse is not a single little a, we can't choose that child.
Cool, so let's think, have we parsed, oops, I just completely changed the string. Have we parsed this little a yet? Have we matched it up to a terminal in the grammar?
Yeah.
No, not yet, right? So we still have to consider this a, right? So does just looking at this a help us distinguish between these two rules?
No.
No.
No, right? Because why?
You can't look that far. The
Still more
machine
possibilities.
can't look that far forward.
Not even about the machine, right? If we just think this a, right? These two rules, remember before we could say, okay, we can determine between big A and big B, right? Just by looking at that first token, right? If it's an A, we know it has to be S goes to A. If it's a B, we know it has to be S goes to B, right? But here, just by looking at this, well, we can say, hey, either of these two rules could possibly match, right? It could be little a, big A, or it could just be little a, right? But if we look one more ahead and we see, in which case, so if we looked, one more ahead and look at these two tokens, right? Then can we distinguish between them?
Yes.
So why is it not the little a? Why is it not this rule?
Because
There's more than one a, right? Yeah, if we choose this rule, we have to stop. And there's no possible way, if we choose this rule, we match the string a. So let's choose this other rule. Yeah.
Isn't it kind of the same concept from the lexical analysis where you're looking for the longest possible match
You
without
say-
any other potentials?
current match would be the little a.
I
And
don't know.
Possible.
That's a good question. I think there are some similarities there, but I'm unsure if it'll cause problems
Okay.
by thinking about it like that.
That's exactly what I was saying. You pick the little a, but you know you still have possibility for the little a, big A, so you can't finalize it.
Right, so if we just chose the little a, right? Yeah. We get here. So is this a valid parse tree?
Nope.
The parse tree? S, A, little a?
Yeah.
Yeah. It's a parse tree that this language can generate, right? It's a valid parse tree. Is it a parse tree that matches that input string? No, exactly, right? Because this represents the string a single A, which is not the same thing as our 4 A's. Exactly. And we can tell that by looking at two characters this time, right? Instead of just one, we can look at two and say, okay, we know it has to be this, right? This has to be the rule that's applied. Now, how much of the string have I parsed so far? Have I matched up in the parse tree with the input string? Just one, right? But I looked at two. So does that mean I consume those two and try to start parsing from here?
No.
You haven't reached the end of the token.
Exactly. So I haven't actually, so this partial parse tree that I've created up to this point, even though I had to look 2 tokens ahead to decide between the rules, right? Even though I had to do that, I know that this token, I know that this one is actually in the tree, right? So I know I've actually parsed this token, but now I still need to match 3 little a's. So then applying that same logic to this a, which rule then do I choose?
it's still indeterminate, so you have to look at the third A and then you pick.
Yeah, we look at the same thing. We look at the two A's, right? And so which rule do we pick?
Little A, big A.
Little a, big A. So how much of the string have we parsed?
2 characters.
2 characters. Are we done?
No.
No.
No, because we still got a big A, right? So now we can do this again. We say, okay, which one applies? By the same logic, right? Little a, big A. And so now I've parsed 3, right, of this string. So now I get to this last one, right? So which of these 2 rules apply?
Little A.
Just little a? Because you try to look ahead and you say, there's no more, we've reached the end of the string, right? There's nothing more there. So we can say it has to be this one, right? It has to be this little a. So now the question, the self-check, right, is to first ask yourself, let's zoom out a little bit. All right, the self-check, right, is this a valid parse tree in this grammar? And how do you know? How can you tell it's a valid parse tree?
Because it ends in all terminals.
It ends in all terminals, yeah. There's all the leaves are terminals. Yep, that's one way. Yeah.
Each subtree corresponds to one of the rules.
Yes, each subtree corresponds to one of the rules, right? Each parent-child relationship, right? Each of the levels of the tree corresponds to one of the rules. So here we go, S produces A. We have the rule S produces A. Here we have A goes to little a, big A goes to little a, big A, and at every level we have that, right? So then we know it's a valid parse tree. Is this parse tree our input string? Is it?
Yes.
Yeah. Right? Our input string was 4 A's. This is the string if we go to all the leaves, right? 4 A's. And so we successfully parsed this string. So we can say, yes, this string was definitely in our input language. Right? This string is one of the strings generated by this grammar. And how do I prove that this is one of the strings generated by this grammar?
By building a parse tree.
Yeah, the parse tree. I showed you the parse tree, right? And you can validate. You can say, yep, all the leaves are terminals, and at every row, at every parent-child, we have an application of the rules. So yes, this is definitely a valid parse tree. All right. Okay, let's look at another example. Oh, I'm zoomed out. Nope, too much. Way too much. Still too much. More or less fine. Okay. So here we have the string, or we have a grammar. So what does this grammar represent? So somebody try to describe this for us in plain English. Let's go in the back.
Strings consisting of an even number of all A's or an even number of all B's.
An even number of all B's and an even number of all A's. I think there's one caveat, maybe.
Has to be at least 2.
At least 2, yeah. Right? Yes, it is. Right? So this is that every A is going to generate 2 A's and a little a, or just 2 A's, right? So it'll be all even numbers. Let's try one. Alright, let's do one that's definitely in that language. Okay. So what do we start our tree at that we're trying to parse?
S.
S. Alright, it looks kind of like a 5, sorry about that. Okay, yeah, it still does. That's fine. Alright, so now, so here's my input string, just 2 A's, right? So, let's look at the first character. looking at the first character, can I tell which rule to apply?
For S, yes.
For S, yes. Why?
Because there's only one way that you have any chance of getting a little a, and that's to choose S goes to big A. And then you have to figure out what to do with that later on.
Right, so if we choose, so it has to be A because A only generates big A's, or little A's. But what about this, if this next character is a B or a C or something?
Well, then the whole string's invalid.
The whole string's invalid, yeah. Yeah, okay, so we can look at this 1A, and this 1A can tell us exactly which one to choose, right? So why is it that we can just look at this 1A and we don't have to look at any of the others? Yeah.
It's not actually true, right? Looking at the 1A allows you to rule out B, but you'll still have to look ahead at the other A to see if either of the rules of big A apply.
Yes, but okay, so that's definitely true. So you're kind of already kind of going ahead, right? Like how are we going to parse this when we get down to here? Right, but I want to kind of think about here, right? Just at this level, at S, how do I decide between A or B? And how can I decide just by looking at that one character? Yeah.
That one character disqualifies B, right? There are no A's and B's.
What do we know about every single string that B could possibly derivate and produce?
There can't be an A, right?
There can be an A, but specifically about that first character.
It has to be a B.
Has to be a B. Yeah, exactly, right? So if I were to think about, if I had a function, oops, that's not how you spell first. Right, if I had a function that took in like a non-terminal in this grammar and was able to calculate what's the first all strings, what are all possible strings, what are the, sorry, let me rephrase this. What is the first character that exists in all possible strings of this language?
Just a little B.
Just a B, right? Right, so this means that every possible string that is derived from a B must start with a little b. Right, are there any other options in here? So how do you know? How do you know that?
Each first character on both sides of the terminal.
Yeah, you can look at every rule, right, of big B, and you can look at this and say, okay, little b, big B, what's the first character that this sequence of terminals and non-terminals is going to generate? It has to be little b. Yeah, exactly, because it seems trivial, right? But, you know. And then you look at the other side and say, okay, little b for this rule. Well, I can also choose b goes to this rule, right? So what's the, what would be the first all characters, all strings that BB generates, what's the first token character terminal that they start with?
B.
Little b, yeah.
And if it wasn't, you just put the or sign and put the other character there?
If it wasn't, so let's say, we could say or C,
The or C there too.
right? So this is a set, so we could just say the set containing B and C, right? So this is all possible characters that strings that B generates can start with. What would be the first of A?
Lowercase a.
Lowercase a? Anything else? What about the first of S?
It's not the,
A, B, or C.
it's gonna be,
We'll get rid of C for now.
it's gonna be A, comma B.
Right? So we know S can go to either A or B, right? So that means if we choose S goes to A, well, since we replace the S by A, then whatever A starts with, S also has to start with, right? And the same way it goes the other way, right? So whatever strings B generates, whatever character they start with, S also has to start with that. So it's kind of crazy. So I just want to reiterate, right? So we're able to, I mean, right now we're kind of doing it by intuition, but we'll see there's actually a way, an algorithm to generate this. But we're able to tell something about basically, so if I call this whole thing G, right? All these rules. What do we know about the language described by G for this set? What are some things we know? Is it a finite set?
No.
Oh, it's an infinite set, right? It contains every possible string of even greater than 2, even number of A's, and even number of B's, right? So this set goes on forever. But with these functions, right, we're able to say something about the strings in this set, right? We're able to say something definitive. We're able to say, hey, every string in this set, right, with S, starts with either an A character or a B character, right? And then we can say, hey, any string derived by the rule B has to start with a B. And any string derived by the rule A has to start with an A. So if I calculate all these, right, now if I have the choice of S goes to A or B, well, how do I know, using these, how can I tell which rule to apply?
Just look at the first
You'll
line.
just look at the first character of the string.
Yeah, look at the first character of the string, and then what do I use of the first sets?
Whichever rule applies.
Yeah, whichever rule applies, right? So I can say, hey, is the first character of the string in the first of A? Then it's got to be derived from that. Is it in the first of B? Then it must be derived from that, right? So this actually helps me choose which rule to parse with. All right, let's look at another example. So what language does this grammar describe in English? Yeah.
A string that starts with A's and then has 0 or more A's ending with either a C or a B.
Yeah.
I think one or more A's.
Well, if it's, I mean, if it starts
You said he starts with 1, so right? It starts with an A, which means it has to have 1 and then 0 or more.
Additional A's.
Yes, yes. So all strings that have 1 or more A's followed by either a C or a B, right? So let's try to parse this, right? So let's have the string. So I start with S, right? So which rule applies?
A or B.
So what did we do before? What was the first thing? How did we kind of try to tell which rule to apply?
Looking at the first character, but that won't help us here.
Exactly. We tried to look at the first character, right? Well, does looking at the first character here help?
No.
Right? So why doesn't this help?
Because both A and B start with A.
Yeah.
A's.
Right? So I actually can't look at only the first character because that doesn't help me choose between these rules. Yeah.
To look for the first non-A character.
I have to look for the first non-A character. And even then, am I done?
Well, the problem with this language is that it could be infinitely long, or at the very least, your worst case could be very, very long. So you would really not want to have to move through the A's from the front. You just want to grab the final.
Right, so part of the problem is, right, is I can't decide. So I could maybe try to say, okay, well I can't decide, so let's try, just for argument's sake, we'll try S goes to B, and we'll try to create a string from that. And so that doesn't parse anything here. Then can I choose which one of these rules apply?
No.
Yeah.
Well, okay.
How many characters do I have to look at?
Two.
2, right? Yeah, by looking at 2 characters, right, I can see, okay, it's gotta be this one. So I go little a, big B. I can do that again, so now I've parsed this one, so now I have the second one, so I can say little a, big B. I parse the second one. Now I try to look at this rule again. So does this rule match either AB or AB? Right? So I say, oh crap, I went all the way, tried to parse this string. What was the one assumption that I made?
That it was going to end with a B.
This first rule, right? So I was like, hey, I can't choose between just by looking at the first character, so I'm just going to choose one. Right? But now I need to backtrack and revisit that choice because, well, I can't parse the string like this, so maybe I have to choose A. Right? So now I have to go back and start this all over again. Start it with A. Right? And then I can decide here by looking at 2, okay, it's got to be little a, big A. And then I can choose it again, little a, big A, and finally I can go with AC. Right? And that's that string AAAC where I've got that there. So what was some of our goals that we wanted from a parser?
Fast.
Yeah.
For it to be efficient?
Is this sufficient?
No.
Why not?
Well, it works out okay if we have 2 possible rules that we have to choose from, but if we have like 30, it's going to take it a long time to guess right.
Yeah, what if I had 2 choices here, right? And here I had 2 choices, and here I had 2 choices, and here I had 2 choices, right? So my number of possible choices explodes, right? It's going to be 2 to the whatever number of choices I have to make, and so I've got to try all possible of those choices until I either find a tree that matches or what?
Spit out an error.
Yeah, it's spit out an error. So I say no tree matches. I tried all possible combinations of the rules, and nothing worked. So if we were to write what's the first set of A?
A, little a.
What about C? What about the C here?
That's not the first.
Right, so every string that A generates, right, has to start with a little a, right? Even though, yes, there is a case where it's going to be a little c followed by it, the fact that there's a little a there means that, right, it's just A. What about the first of B?
Also A.
Also A. So then what was the problem here? Why couldn't we decide? By looking at that first character.
The endings are different?
Because what?
The endings are different?
The endings were different, specifically with the first sets, right? We couldn't tell just by looking at that first character, because in the first set of A and the first set of B, right, their intersection, they have an overlap there. So if we see an A, we have to say, oh, it could be either from S goes to A, or it could be from S goes to B. Let's see. Okay. So now I want to go over how we're actually going to build a parser to look like code. So let's go through an example and then we'll kind of walk through one. So the idea is in top-down parsing, so we want to build these parse trees. Right? Because the parse trees represent the way the rules are applied. When we actually create these, we're going to want to essentially write a parser, and our parser is actually going to mimic the tree itself and the structure of the calls. So we'll look at this very quickly. So we have, or not very quickly, but we'll definitely look at this. So we have a grammar here. S goes to big A, big B, big C. A goes to little a, B goes to big B, little b, B. And C goes to big C, C, or epsilon. So what's the language described by this grammar?
The string is empty, a single A, any number of of little b's, or any number of little c's.
Yes. Is that right? How come you can just have one C? Can you have one C?
Yes.
Yeah? Why?
Because epsilon concatenated with any character is just
Yeah. Right? So we can first say C goes to big C, little c, and then the next time we say that big C goes to epsilon, and we say epsilon concatenated with C is little c. Perfect. So what we're going to do, we're going to write a function for each of these rules, for each of these production rules. So what's the first set of big A?
Little a.
Yeah. Just little a, right? There's only one possible string that A can generate, and it's little a. What's the first set of B?
Little b.
Little b. What's the first set of C?
Epsilon or
Little c.
Yeah, epsilon or C, right? Because C could generate nothing, right? So we have to keep that in mind. So based on what we looked at before, can I efficiently decide from S? Can I efficiently decide between which rule to parse for S? How? Was it?
Each of them are different.
Right, yeah, each of the first sets are different, right? There's no intersection there. So, to write this in code, it follows pretty much exactly from our intuitions from this. So we first say, okay, what's the get token function?
Returns the first token of the string, of the input
Yeah.
string.
Parses the input string, returns the first token. Right? This is exactly the same semantics that you have in lexer.c, right? That you've been coding against and using in Project 2. This is why you do that, not just because we like it. So what do I know? How do I check if I have rule big A applies?
you look at the token type.
I look at this T type, right? I look at this token type. What am I checking?
Token type is A.
If it's A, right? If it's A, then what? So what do we know about get token from the lexer? What are the semantics there? So it returns the token type, right? We already said that. What else does it do?
It also stores whatever token value,
It stores the token value,
whatever line it was read from,
stores the line.
and there's one other thing.
What does it do to the string? Yeah.
It like eats the first bit of input.
Yeah, it eats the first token from the input, right? And moves the parser, the lexer forward through the input, right? Because it made the decision to parse that token, right? And so next time you call get token, it starts after that input, right? But if we think about our tree, right, that parse tree that we want to create, have we actually parsed little a here? Does S generate little a?
No.
You're shaking your head. Why are you shaking your head?
Because someone's saying that it could possibly parse the way, or parse A.
Yeah, so it doesn't say, right? The only rule we have right now we're just concerned with parsing S, so we need to decide which rule to apply, right? Big A, big B, or big C, right? But neither of these actually generates a terminal, right? None of these rules generates a little a. So in our tree, right, we have S goes to big A, but we haven't actually created that leaf node for A there, right? Because this rule does not parse that. And so if we don't want our token to be consumed yet because we haven't actually matched it and parsed it, then what do we have to do with the lexer?
Advance it.
What's that?
Not get the token.
Yeah, we want to put that token back, right? And say, okay, we're not really ready to actually parse this because S goes to A doesn't generate any terminals, right? I just had to look ahead and kind of peek at the next token to tell which rule to apply. But now I've decided, right? I know it's in little a, so I know it has to be S goes to big A. But I'm going to let parse A figure out how it wants to handle that. So then we're going to call parse A, right? And parse A is going to be very similar. It's going to make sure that it parses everything. What else do we know after we've parsed A? What do we know about the input string or the input?
We're done.
Yeah.
it better be done, right? What if there's more after we try to parse A?
We have an error condition.
Right, yeah, that string is not in our language.
So if we get token again, if we set our t-type equal get token, if that's not end of file,
Then we know there must be a syntax error, right? That we know that this string did not come from this language. Right now we're going to abstract this into like just a check end of file function that reads from the token exactly that, right? Reads from the token and say, is it the end of file? If it's not, then throw an exception, throw an error, or say that there's a syntax error. So what's the next t type we want to check of this get token?
check
So
the t.
checks if it's B. So what's the first thing it's going to do?
Unget the token.
Unget the token. And then what?
Parse B.
Parse B. And then what?
And then
Check
check
the
Check for end of
Check the end of the file. So what about the next one? What if it's a C?
same thing.
if it's C
Or epsilon.
or epsilon.
Can you read in an epsilon token?
It's empty.
What's your lexer? What are the types? What things are your lexer going to return when you call get token?
Tokens.
So you're going to return token?
I think it could return. Just from where.
Oh, because you're trying to. It's a,
ID and number tokens, yeah. So it's going to return one of your tokens that you've defined. What else?
Use the length.
What was it?
The length.
The length? No. Kind of.
Value.
Value?
well, the problem is you don't put epsilons in your, generally, you don't have epsilons in your string because you could have like, if you they get abstracted away.
Exactly. Yeah, you don't have epsilons in your strings, right? So your token, your lexer, so you've read the lexer.c code, right? It returns either the token, right? What is this check EOF looking for?
For the end of the file.
The end of the file, right? That's a valid thing that your lexer returns. It's checking for the end of the file, right? So end of file is kind of a meta token or a token that represents that you've reached the end of the input file. What's the third one?
Error.
Error, right? Yeah, if you've read an error token. But can you check? So none of those are epsilon, right? None of those three are an epsilon. So let's check. Okay, so if this token type is a C, right? Then how do we parse this?
Get token.
Parse
Parse
the end.
check part.
And then we parse.
Yeah, we want to unget the token. Want to call parse C again, and then what do we want to do?
Check for file.
Check for the end of file to make sure.
No, it shouldn't.
But we need to make sure we match one other string, right? What was it? So each of these cases, what are the strings that each of these cases match? What was it? Yeah, strings that start with A, strings that start with B, strings that start with C. Is that all of the strings that this language can generate?
No.
There's also
Which
the-
string is it not matching, or what string?
Empty string.
The empty string. So how do we know from what the lexer returns, how do we know if it's the empty string?
If it's end of file,
If it's end of file, why?
because it means it's saying I didn't receive anything, which
Right.
is equivalent of saying
Nothing.
empty string.
Yeah, so let me check if it's the end of file, right? And actually I need to update this. It's super annoying. I should actually put that in here, but we'll see other examples as we go forward. Because we still, so can S itself generate an epsilon? No, right? Just like S itself didn't generate any little a's, S itself didn't generate any little b's or little c's. So actually this is incorrect because S shouldn't be handling the case where it's an end of file. Right? Who should handle that?
Parse C.
C, because C knows what to do if it's an end of file, right? Or C knows what happens when C goes to epsilon, right? S doesn't have to worry about that. The only thing S has to worry about is S goes to big A, S goes to big B, S goes to big C. Those are the only things. S is only deciding between those three cases. That's it. All the other languages are going to decide that. So what if it doesn't match any of these three or four cases?
Throw error.
syntax error.
So what is?
This part should be exactly like this part. And actually you can put these in the same thing here. You can say if t-type is C or t-type is end of file. Make a note. So note from this, right, that so the only reason we're able to do this, right, to look one token ahead and be able to decide which rule to apply, is because, right, we know that the first of A, the first of B, and the first of C, they're all disjoint, right? They have no intersection, no overlap here, right? But we can still write this in a similar style of, hey, try to parse A, right? And if A says, hey, that's not a valid A, then you could try to parse B, and then if it says, hey, that's not a valid B, you say, okay, then try to parse C. Right, so you can implement a backtracking parser very easily. But if you have a language like this where you can tell right off the bat, then you can make it a lot more efficient. And so that's the idea of these, what we're going to call predictive recursive descent parsers. So recursive descent just means that we're going from the top down, right? And we're recursive because we're always calling this parse S, parse A, parse B, parse C functions. What does predictive mean?
We're predicting which branch S is going to take based on some parameter.
Right, so we're predicting, and what we really want to do, so it's predictive because we want to be efficient. And the key point is that we're going to be efficient because we're only going to look one token ahead. And that's going to tell us exactly which way to go. So are all grammars, can all grammars support a predictive recursive descent parser?
No.
Why no? Could you give me an example of a grammar that does not?
If you had one that you needed to to tell the difference, you needed to look multiple tokens ahead.
Did we look at any of those examples today?
Yep.
Which one?
The ones that we were looking at the end, whether the difference was B or C.
Yeah, the ones that ended with either a C or a B, right? So we couldn't, just by looking one token ahead, we can't tell exactly which one to take. And so, what helped us kind of determine if we could actually support this kind of a parser? Yeah.
Like looking at the first characters that each rule could produce.
Exactly, looking at the first characters that each rule can produce, right? If they can each produce distinct characters, then clearly we can tell just by looking at that one, right? I mean, it's kind of almost a recursive definition, right? It's like we want to be efficient, so we want to only look one character ahead. So how do we know? Well, we know if each of the rules looking at one character ahead if they're all distinct and disjoint, right? So that's why we're going to use this first function, and this first function is going to be defined, so this is just, we're being a little bit more specific here. So the idea is that, so alpha, you're using alpha here to represent a sequence of terminals and non-terminals, right? So we ask what's the first of little b, right? So we can say it's clearly little b. Or what's the first of little a, big A? Well, it's clearly just A, right? So it can be any number of sequence of grammar symbols, and then it returns a set of terminals and epsilons. So this is something you should keep in mind because this helps you think about what the type of the first function is. So that when you're doing this by hand, right, you can say, okay, the inputs is a sequence, and it's a sequence of terminals, non-terminals, and epsilon, and it only returns terminals and epsilons, right? So if you're trying to compute first and you get a big A or a big B, some non-terminal in there, you know you've made a mistake, right? So this helps you to self-check that. Okay. And then on Wednesday we'll look at, this isn't the only thing we need, and we'll look at why we need that and what other functions we need.